Situations where fluids flow through pipes or tubes are enormously important to industrial processes, our economy, and our biology. So let's lay down some of the definitions and conclusions and applications that we can get from applying basic physics principles to fluids flowing through pipes. We're going to begin with some definitions. Imagine a pipe or tube with some known cross-sectional area, A. And there's some fluid in this tube with a density that we'll symbolize by a lowercase Greek rho. And in this video, we're mostly going to be concerned about how the fluid might flow or move through that tube. So we have a quantity called the fluid flow speed or velocity. We'll use those interchangeably here, but we'll treat it as a scalar. The fluid flow speed is, imagine if you dropped a speck of dust or a little float in this fluid and watched it go along from one side to the other. The speed that that parcel moves at with the fluid is the speed of the fluid flow. So even though we can't maybe see if the fluid is transparent, we can't see it moving. If we drop some dust in there or glitter or something, we'll see this flow velocity show up. So these are the basic things we can use to describe a fluid flow through a pipe. Now there's one other measurement that we'll get to later. But this is a measurement of pressure. And the pressure in fluid flow is measured in the condition of, it's called ambient condition, where the pressure is just off to the side. We often think that, the fluid comes blasting down this tube and it hits the end of the tube and pushes on it, and that causes a lot of pressure. That's not really what we're talking about here with fluid flow pressure. It's not a pressure gradient that drives the fluid from left to right. It's just the pressure that would exist if, say, a hole was poked in the tube at some point and the fluid came spurting out. So that's what we mean by fluid ambient pressure. So these are our basic measurements. Now there are a couple of quantities that we can derive from these. So let's give the symbols for those. The first derived quantity is called the mass flux. The symbol is J, and this is equal to the density times the flow velocity. So why would someone be interested in the mass flux? Well, if we take the density, which is kilograms per meter cubed, or mass per volume, and we multiply it by the flow velocity, meters per second, or distance per time, we have three products of lengths on the bottom to get volume and one length on the top to get distance. So these two cancel, and what we get is mass over time over area. So in SI units, this will be kilograms per second per square meter. And so this mass flux represents how much mass would flow through the pipe in a given amount of time per square meter of area. So a larger mass flux generally means there is more flow through the pipe, independent of how large it is. The next quantity called the mass flow, and this is just the actual amount of mass that passes a point in the pipe per unit time. So we take the mass flux J and we multiply it by the cross-sectional area A, and then this gives us sort of the mass per unit time. So the overall flow rate through the pipe, how many kilograms of water end up on the end of the pipe versus the amount that came in the beginning if it runs for a specific amount of time. Okay, so those are our definitions here, things we can measure, and the two things that we can calculate from those. Now, we haven't applied any physics yet. We've just kind of made some unit analysis. So our physics is going to come from two principles. Two principles for fluid flow. The first one of them is conservation of mass. So as the liquid or gas flows through this tube, it can't have any mass created or destroyed. The same number of kilograms that go into the end of the pipe must be the same as the number that come out of the other end of the pipe. So we have a condition that the fluid mass flow rate, F, should be equal at all cross sections of the pipe. So no matter how big it is or how fast the fluid is moving, or even if its density changes, if you put up a gate and count how much mass goes through that cross section of the pipe, it should be the same at any place. Okay, so we can write this out as the density times the cross-sectional area times the flow velocity at one point, the location 1, should be equal to that product of three things at any other location, like location 2 or any other location in the pipe. So that quantity is a constant along the entire flow. The second main principle for fluid flow is conservation of energy. Now, as long as the fluid is flowing in a pipe and it's got a smooth, well-defined velocity value, if velocity is not varying greatly from point to point, if it's mostly a uniform velocity field, then we can simplify the conservation of energy equation to look like this. 1/2 v squared at some point plus gh plus the ratio of the pressure and the density, we'll see how that comes out in a second, is a constant. So at any compare any two locations on a pipe, whether it goes up to a different height, and there's an H1 and an H2, or whether the pipe has a constriction to a different cross-sectional area, A1 to A2. The velocity of flow and the pressure of the flow and the density of the fluid must change according to this conservation of energy equation. All right. Now, the way that we get this equation doesn't maybe look exactly like conservation of energy for a single object. We have this term involving the pressure and density in there. The way that we get this is a little bit involved, but I will try to go through a proof of this equation. This equation is called, has another name. It's called Bernoulli's equation, if you go to look it up in some other source. That's called Bernoulli's equation, and it's basically a statement of conservation of energy. All right, so let's take a little bit of time here, since we're trying to show how these come from fundamental physics principles. Let's try to derive Bernoulli's equation for flow in a pipe. And we'll consider the situation where the area might change over the length of the pipe. We don't need to. The The case where the height changes is really much simpler. That could just be, it's the same result as if we had a fluid statics, right? P and rho GH go together and cause that change in pressure for a change in height. That's the same thing happening there as happened in fluid statics. But with flow velocities in here, it's a little bit interesting how this equation actually comes about. So we're going to start with the idea that we've got this pipe, and it begins with some area, let's say A1. Then it has some constriction over some middle portion of the pipe, and then at the end it ends up at final area A2. So this change in areas, it sort of happens near the middle, and far to the left and far to the right, the pipe is again having a constant cross section as the fluid flows through it, right? So how do we apply conservation of energy to this situation? Well, we can't rely on the volume that goes through the pipe of the fluid, because the volume might change, right? The density is not necessarily constant here, but what won't change is the amount of mass that flows through the pipe. So we use the principle of conservation of mass, and we sort of watch a given mass of fluid as it goes from the left at A1 all the way down to the right side at A2. So what's going on there? Well, we've got some energy here, right? We have some kinetic energy, 1/2 m times the flow velocity, v squared, right? The mass is actually moving over here. And then over here we have some kinetic energy also, 1/2 m v2 squared. It's the same chunk of mass of the fluid, the same atoms that we watched over on the left. Now they're over on the right, and they're going at a different speed, v2. They have to be going at a different speed to maintain the conservation of mass equation, right? We have A1 rho 1 v1 equals that fluid flow rate on the left, and A1 A2 rho 2 v2 equals that fluid flow rate on the right side. Okay, so if there's a constriction in an area, then it's quite likely that this speed v2 will be different. So this is the kinetic energy of the fluid on the left, and here's the kinetic energy of the fluid of the right, and those are not equal. So the kinetic energy doesn't stay constant of a bit of mass as it moves through this constriction. It turns out that it actually goes up, because V2 is going to be higher if A2 is smaller. So what we've got here is a situation where the change in the energy occurs due to some work being done on the fluid that we haven't yet considered. So we don't have a constant energy here. We can't. So there must be some work coming from somewhere. And the source of this work is actually the pressure force of the fluid on itself. So if there's a pressure over here, P1, that's going to push this mass to the right. And if there's a pressure P2 over here at the end, that's going to oppose the motion of this mass. It's going to force it to the left. So how do we calculate this work? Well, it's composed of two parts. As this piece of fluid moves all the way over here, it's going to feel a force from the left of P1. And so this is going to be composed of two parts. A work done on the left side by the pressure, and the work done on the right side of the parcel of mass by the pressure. So we have two of those. And this work is caused by how the pressure varies from P1 to P2 as the fluid moves. So remember, work is force times distance, but that's only true if the force is constant. So here we have a force which may not be constant, so we have to take an integral. So we go from 0 to L. That's the distance from the start to the end. Here we have the pressure at a given x coordinate along the pipe. The force is equal to pressure times area. And then we integrate that over distance. So this is WL. And then we have WR. All right, well, the left side of this parcel of fluid goes from 0 to L, but the right side doesn't, right? It starts over here. It goes from some thickness of the chunk of mass over to this point here. So the right edge of the parcel of mass goes from some spot which we'll call lowercase l1 over here, then it goes to L plus lowercase l2. So L2 will be the length of that chunk of mass on the right, and L1 will be the length of that chunk of mass on the left. So over here, for work right, we've got a L1 as our starting point for that for that right edge, and then it goes to L plus L2. And we're talking about the same functions for pressure and area as it varies along the pipe here. But this time, the pressure is pushing opposite to the motion, so we have a subtraction. Okay, so that's the two amounts of work done. Now what you notice here, these integrals, the limits actually overlap quite a bit, right? L1 is close to 0, and L2 is just a little bit bigger than L. So there's this big chunk in the middle where they have the same, they cover the same sort of x, range of x values, and one is plus and one is minus. So there's a lot of cancellation there. So if we take that into account with the limits, it ends up that we only have to integrate this pressure function from 0 to L1. That's the part that's not killed off by this second integral. So we have 0 to L1 of P times A. And then we have to integrate from L to L plus L2 on the second one. So L to L plus L2. All the rest of this is subtracted off. So that's P times A at those x positions over there on the far right. Okay, so we're almost done now. We used now the fact that the fluid, the pipe on the far left is basically constant pressure and constant area, and the fluid on the far right is at some pressure and some other area. And these functions only change kind of in this middle region. So way on the left, when we're doing this, P and A are basically constant and equal to P1 and A1. So we get P1, A1, L1, right? A constant integrand just gives us the value times the limits. And then on the left, we get P2, A2 times L2. So again, there's a rectangle of height PA and a width of L2 overall. Okay, so this is our formula from calculating the work. And then our last bit here to notice is that area of this chunk of mass, the cross-sectional area, times L1 is merely the volume of that chunk of mass on side 1. So we have P1, V1 on the left, and on the right, the same argument applies. We get P2, V2. Okay, so that pretty much completes our proof. We're going to do a little bit of simplification at the end, but let's summarize this work calculation here on the top. What we get is 1/2 m v1 squared minus 1/2 m v2 squared. So change in kinetic energy from situation 1 to situation 2 must be equal to this, actually it's final minus initial, right? Final kinetic energy is situation 2, initial is situation 1, because we went from left to right. So that's equal to the work done, which is P1 V1 minus P2 V2. So it seems like this product P times V can be interpreted as some sort of energy of the fluid. It actually is similar to the internal energy of the fluid, that's ability to do work on itself via its pressure. So to write this as a conservation equation, we want to move all energies at the same location to the same side of the equation. So when we do that, we'll have 1/2 mv2 squared, and then we'll move the P2 over here, so P2 V2. And then we'll move the kinetic energy to the right side for situation 1. All right, and we're almost done. The last step is we would like to make this independent of a particular size of chunk of fluid here. We want it to be independent of the value of m. So it's the same mass that goes in on the right, that comes out on the right, and goes in on the left. So we'll divide the equation on both sides by m. That can cancel it from those v squared terms. But then it puts the m on the denominator in these pressure times volume terms. It's the same m both places though. The volume is different. But what we've got here then is mass divided by volume, and mass over volume is the same thing as density. So that's how we get density in there. Mass over volume, that's going to be rho 2 there, and mass over volume 1 is going to be rho 1 there. So that's our derivation of Bernoulli's equation, at least for the case of horizontal pipes. Right? If we had a vertical segment to our pipe and there was a change in height, then our energy expression would change from 1/2 mv squared to 1/2 mv squared plus mgh. And then we would get this height term in here, gh, on both sides. All right, so that's our Bernoulli's equation and how we derive it from fundamental physics principles: conservation of mass, conservation of work energy theorem, and calculation of work from the force due to pressure. Okay, now let's look at some applications of this. All right, so one very important application is a device called a Pitot Tube. Kind of a funny name. But there's no doubt that you have actually relied on one of these at some point in your life. Maybe not directly, but you relied on someone who relied on this device. Because this device is used to measure the speed of objects traveling through the air, such as airplanes. All right, so here's what the Pitot Tube looks like. I'll explain what I'm drawing here in a second. Okay, so we have a set of concentric tubes here. There is a central tube which just sits in the stream of fluid flow. So we have some air, or I suppose you could use this with water too. So we have some fluid flow past here. And this little tube sits there with this front opening facing into the fluid flow. So the fluid then runs into this tube and comes down to one side of a pressure meter. Of course, when the fluid is in this branch, which I'll call branch 1, it's not nowhere to go at the bottom, so its velocity is 0. And it can't move through that tube because the velocity is 0 at some point. So conservation of mass implies that no more mass can go in. All right, so that's the first tube. Then the second set of hollow tubes is concentric. So there's a cavity here, sort of all the way around the outside, which has some openings that are parallel to the fluid flow. So that tube is connected to this other side of the pressure meter, delta P. But this tube senses the pressure of the air that rushes past it. So V2 is equal to the speed of the air. All right, now if the air is moving at all, a difference in pressure is detected at this pressure gauge down at the bottom. And we're going to use Bernoulli's equation to relate that difference in pressure to the air speed. All right, so we've got a fluid flow here, the flow of the air past the pitot tube. That means we can apply Bernoulli's equation. So 1/2 V1 squared plus pressure 1 over density 1 equals 1/2 V2 squared plus P2 over rho 2. Everything is horizontal here, so there are no H's necessary. And let's just note a couple things here. So first of all, for air flowing here, if there's not a large change in temperature, then there will not be a large change in the density. So we'll have a density here which is roughly constant. So we'll just call that rho of air, and we can look up value here. It's about 1.22 kilograms per cubic meter for ordinary air on Earth. All right, the second thing we'll note is that V2 is larger than V1. The flow velocity up here is equal to V air, V1 is 0. So therefore P1 is larger than P2. Okay, so the flow, the air that's moving has a smaller ambient pressure. So our delta P, our difference in pressure, is going to be equal to P1 minus P2. So we'll solve for P1 minus P2 in this equation up here. All right, moving the P2 to the right side, we'll have these divided by the same density rho of the air. And then on the left side, it will be the difference 1/2 V2 squared minus 1/2 V1 squared. All right, so then we have delta P over rho of the air. And then for our velocities, V2 was the speed of the air flow and V1 was 0. So we have 1/2 V air squared. Final step is to just solve for the velocity of the air explicitly. And this gives us our formula for using a pitot tube to measure air speed. So they put these on aircraft. You can look, next time you go to the airport and board one, you can look on the outside of the plane and you'll see a bunch of these little, they sort of look like hooks that point forward, sticking up from various sides of the plane. And what those are is pitot tubes that are used to measure the air speed. Of course, to be accurate, you have to account for how the density might vary at given altitudes, but they know how that works and they can calculate the flow speed. All right, so let's do an example with some numbers here to get a feeling of how this works. Let's say we set up one of these pitot tubes and we measured a delta P value of 60,000 pascals in air. And how fast would that air be flowing? Well, let's just plug these in. Use our density of air. And if we do that calculation, we're going to get 313.6 meters per second. All right. So that's a pretty fast airflow, but it's not too fast to use Bernoulli's equation. If you got a flow speed that was, say, larger than the speed of sound, which is about 340 meters per second, you would have some more questions to answer about how that was happening. It's also a good exercise for you to make sure that these units verify down to meters per second. Remember, pascals are newtons per square meter, and newtons are kilograms times meters per second squared. So we should be able to simplify that and verify we do get meters per second at the end. All right, our next example application of fluid flow is called a Venturi tube. And a Venturi tube is a device which is used to measure the rate of fluid flow, chiefly in a pipe. So the way the Venturi tube works is we place a constriction in the pipe, a smooth constriction down to some smaller area, A2, which is less than the normal area of the pipe, A1. And what this does is it causes the fluid to flow faster through the constriction due to conservation of mass, and therefore have a smaller pressure at A2 compared to at A1. So we measure the pressure difference between these two locations with a pascalometer or a manometer. And that pressure reading can ultimately tell us how much fluid is going through this pipe per unit time. So let's see how that works out. Okay, so here we'll have a V1 value, we'll call that. And here we'll have V2. And so our application of Bernoulli's equation has us calculating 1/2 V1 squared plus P1 over rho 1 equals 1/2 V2 squared plus P2 over rho 2. Now, in this equation, we have more unknowns than we would be able to solve for. So we need something else. And the second ingredient is the way that the velocity and area correlate. So the conservation of mass equation. All right, so as the area gets smaller, the speed goes up, and then that's going to influence the pressures like this. Okay, so we actually have basically a system of equations to solve here for the unknowns V1 and V2. All right, so I'll save us some time on that. The first approximation that we usually make with liquids the densities of liquids don't vary all that much as they flow through pipes. You know, they're not really getting much hotter or colder, so their densities will stay roughly constant. And that means that we can solve for, let's say, V2. V2 will be equal to V1 times the ratio of A1 to A2. A1 is larger than A2, so V2 is larger than V1. The second thing we can solve for is the delta P. Using Bernoulli's equation, note that V2 is larger, so P2 is going to be smaller. So our delta P is P1 minus P2. That's a positive difference, and that's going to equal to 1/2 rho times V2 squared minus V1 squared. Okay, so our step now is to substitute for the variable V2 in the equation for delta P so that we can remain only with a V1 in the equation. So we'll have 2 delta P over rho equals V1 squared times the area ratio squared minus V1 squared. All right, so then we can solve that for V1. It will be 2 delta P over rho times the area ratio squared minus 1 as a quantity, and then square root of the entire fraction. Right. Okay, so that's our way to predict the flow speed from a Venturi tube measurement. We need to know the area of the pipes before and at the constriction. We need to know what fluid we're talking about, the density. The density comes in here and that matters. And we need to measure the pressure difference. But if we do that, we can tell how much fluid, how quickly the fluid is flowing through the pipe without, like complicated things like paddle wheels or pumps and pistons and things like that. It's sort of a passive measurement, which is useful. So we got that formula for V1 figured out. Then to find out the flow rate, we can just take the area times the density times that velocity. So that can give us the flow rate. All right, so let's do an example with some numbers here. Let's say we were looking at some water or a similar fluid like juice or soda flowing through a pipe like this. And in this setup, we measured a delta P value of 4,000 pascals. So our density to use for any type of water or related food product drinks is, if it's so close to water, we just use the density of water for those. And let's take it as a given that in this system, the constriction had a cross-sectional area of 10 centimeters, 10 square centimeters, and the regular tube A1 had a cross-sectional area of 20 square centimeters. Okay, so we calculate from that the flow velocity. We would get 2 times 4,000 pascals over the density is 1,000. And then our area ratio is a 2-to-1 ratio of areas. You'll want to watch out when you're doing homework problems. If the pipes are circular, they may provide you with the radius or the diameter, and you need to get the area from that first. So here I've just given you the areas, so I can say the area ratio is 2-to-1, and that ratio squared is going to be 4. So down here we'll have 4 minus 1. And if we work out that numerically, it comes out to 1.633 meters per second. And plugging in the area and velocity of location 1, we can get the flow rate as 3.26 kilograms per second. All right, so kind of a slick way to measure how much fluid is flowing through a pipe, very passive. You just set up these pipes off the side and put a little pressure detector there, and you can tell, roughly more or less how much fluid is going through there. I will point out to you that if you ever get involved in actually measuring flow rates, that a Venturi tube is not remarkably accurate. Usually it is better to use some sort of vaned pump. That's what they use at gas stations because people are very particular about how much gas they get and how much they get charged, right? They have even hundredths of a cent there sometimes. But this is a good application of basic physics principles to fluid flow through pipes. and we can turn this into some useful measurements and predictions. All right, so that basically covers what we're going to learn about fluid flow. We have conservation of mass, conservation of energy, Bernoulli's equation, and how to apply those to some basic applications of fluid flowing through pipes.